if instead of only one sphere we have n spheres, the total volume is now equal to n, capital N, let's say n is the number of spheres, times phi, where remember that we defined phi last time. This was equal to 4 pi over 3 r cubed, where r is the radius of the small sphere, let's say. Then we also have the volume 4 over 3 pi r prime cubed, which is the volume of the large sphere, let's say. And we calculated the heat generated in this volume last time, and therefore the total work in this case can be written like this. We have two. Remember last time what we derived. We derived the formula like written like this. It was 2k delta squared v plus phi over 2, where delta squared was a squared plus b squared plus c squared. And now that we have n spheres, this formula will become like this. It will be 2k. Then we have delta squared, and then here we have the volume v, which is still the same, plus instead of phi we have n times phi, because this is the total volume of the small spheres. And we will assume that n times phi is still negligible with respect to v, and we have to divide this by 2. And Einstein also rewrites this formula like this: 2k delta squared v times 1 plus phi over 2. In this case, this is lowercase phi, and lowercase phi is defined as n phi, capital Phi, divided by the volume. So this represents the fraction of the volume occupied by the spheres, the small spheres. And besides delta, I want to define also delta star, whose significance I will try to explain in a moment. It is equal to a star squared plus b star squared plus c star squared. These constants, the dilatational constants, a star, b star, and c star, will be different from a, b, and c, as defined previously, because in this case we have more spheres, and I will try to tell you why this is the case. This is also what Einstein addresses. A star in general can be calculated like this. It is the derivative of the velocity along x, along xi if you want. That's the x direction. So we take the derivative with respect to, let's call it x, and I will show you why in a moment. And we have to calculate this at the origin. If you remember, without the presence of the sphere, u was written in this form. It was written as a times xi, and this was a times x minus x0. So the sphere was centered at x0, but in this case we don't have the sphere. You can see that in this case du over dx gives us the constant a. But with the presence of the spheres, we have something different here. So the calculation is different. We have to calculate this derivative at the origin. With the presence of the sphere, in this case, instead of having xi, we have another part that we called u1, and we also found this expression. But if you calculate the derivative of u with respect to x, and with only one sphere, you calculate this at x equal to x0 in this case. Or if you want du dxi at xi equal to 0. This is another way to calculate a, because the derivative of u1 with respect to xi, if you go back and check the expression for u1, actually you just have to check the expression for u, the overall expression with also the presence of the sphere. You can see that if you calculate du over dxi and you set xi equal to 0, you will get a. However, Also with the presence of one sphere, if we define du over dx calculated at x equal to 0 as a star, well, in this case, a star will not be equal to a. This is a coefficient related to the dilatation along the x-axis or xy-axis, whatever you want to call it. And this is what we want to find. In general, this is the definition that we will use. This will be equal to A only without the presence of spheres, without, let's say, spheres, just like this. But now I don't need to write this down. I will write it only after I consider all the n spheres. So let's get back to the n spheres. With the presence of more spheres, we are going to get more contributions to the formulas. In particular, let's write the formula for u. We have a times x. In this case, I will use x, not xi, and I will try to explain in a moment. Just wait. And then we have minus a summation of terms over an index that I will call nu. And then here I have a very similar expression to the expression that we found earlier. So we have a xi nu squared plus b era nu squared plus c zeta nu squared times xi nu, and here we have 5 over 2 r cubed over rho nu to the fifth power minus 5 over 2 times r to the fifth power divided by rho nu to the seventh power. And then we also have minus r to the fifth power over rho nu to the fifth power a times xi nu, like this. And you can see that if you consider this formula here and you simply neglect the index nu, so you just call this xi, you just call this era, you just call this zeta, you call this xi, and so on and so forth. Also this one, you will call it rho. You will get the usual formula for u1 with this minus sign. If you go back and check the expression that we found for u, we had this formula. So maybe I can also write it down for the sake of convenience. We had a times xi minus, we had a xi squared plus b era squared plus c zeta squared times xi 5 over 2 r cubed over rho to the fifth minus 5 over 2 r to the power 5 over rho to the seventh minus r to the power 5 over rho to the fifth a xi. So we wrote it like this, where xi was equal to x minus x0. x0 was the x-coordinate of the center of the sphere. The sphere was centered at the point x0, y0, z0, and era was y minus y0, and similarly zeta was z minus z0. In this case, we have more spheres, and therefore we have to consider the origins of different spheres. So xi nu will be x minus x nu, where x nu is the x-coordinate of the nth sphere, if you want to call it that. And similarly, era nu will be y minus y nu, and zeta nu will be z minus z nu, like this. So this is very similar, and rho nu will be simply equal to the square root of xi nu squared plus era nu squared plus zeta nu squared. Simple as that. And here, instead of putting xi, we will have to put just x, because we do not know what to put for x0. I mean, in here we had xi because we only had one sphere, but in this case we will only have a times x, like this, written like this. This is a solution to the more general problem. And of course, we have to assume that the average distance between spheres is large compared with their radius. So that's why we can sum all these expressions, because otherwise this expression would not hold if the spheres are very, very close. Anyway, returning to the discussion of this x here versus this xi, that's not important in what we want to do here, because that would just be a constant. So you could also add a constant to this velocity component, but the stress components will not change because they will contain derivatives of the velocity. So the constant terms will vanish when you take derivatives. So these are not important. I mean, a times x is important, and it is also contained here because we have a times x minus x0. But this x0 is not important, as I said, because it will give no contribution to the work, because in the expression for the work we have derivatives of the velocities, and therefore that's not important. So as I said, the center of the new sphere will be at x nu, y nu, and z nu, and we want to find a star. The dilatational coefficient in this case will be a star, which is equal to the derivative of u with respect to x evaluated at the origin. From the expression of the velocity there, this will be equal to a plus, and then we have some summations over nu of the derivative of u nu with respect to x evaluated at the origin. So what we called u nu here is simply this one highlighted in red with this minus sign as well. So we have to put this minus sign there as well. And this is approximated by Einstein because if we use this formula, we cannot really find a closed form expression for a star, a simple expression for a star. So for the sake of convenience, Einstein assumes that these spheres are continuously, quote unquote, continuously distributed, and there are lowercase n spheres per unit volume, and lowercase n is a constant. So this is an approximation, of course, because the spheres are not continuous, but this allows him to write the formula in this manner. A plus, instead of a summation, here we have an integral, which is multiplied by lowercase n, which is the number of spheres per unit volume. Do not confuse it with capital N, which was the total number of spheres, whereas this is a number per unit volume. And then we integrate the derivative of u nu with respect to x evaluated at the origin over the volume, and this is equal to a. Now we can also take the derivative of u nu with respect to x nu, but we have to change the sign because this is a function of so xi nu is x minus x nu. So if we take the derivative with respect to x nu, we have to change the sign, and this will be a minus n integral du nu with respect to x nu evaluated at the origin dv. Now the differential of the volume can be written as the differential of the surface, and we multiply by the differential of the radial distance rho nu. This is as if we were using spherical coordinates, and in order to calculate the integral, indeed, we will resort to spherical coordinates. And let's rewrite this. This is a minus n integral, and then instead of du nu with respect to x nu, I will rewrite du nu with respect to rho nu, and then I use the chain rule, d rho nu with respect to x nu. We still have to evaluate this at the origin, and then I have d rho nu ds. So I rewrite it like that, and now I also have that d rho nu over dx nu. This is simply equal to x nu divided by rho nu, according to the expression for rho nu. Why is that? Well, because we have to take the derivative with respect to x nu of the square root of x minus x nu squared plus y minus y nu squared plus z minus z nu squared. So the derivative of this is 1 over the twice the square root of x minus x nu squared plus, then you have y minus y nu squared plus z minus z nu squared, and then you have to take the derivative of this expression. So you have here you have derivative with respect to x nu of x minus x nu squared, and this is simply equal to, so this derivative here is twice x minus x nu times minus 1 if you want. So let's rewrite this derivative. This denominator here, this part, is equal to rho nu, so we get twice x nu minus x over rho nu, twice rho nu, so we simplify these two, and remember that we have to calculate this at the origin, so we can also set x equal to 0. We can set x equal to 0, right? And therefore this is what we get, this expression here. And finally we can also put together this derivative with this differential, and that will give us the differential of the velocity. So I can rewrite this as a minus n integral, I have du nu times x nu rho nu, and then I have ds like this. And after I integrate first over this velocity here, I can write this integral as a minus n integral u nu x nu over rho nu times ds. And we have to evaluate this velocity here at the origin. These last steps can be motivated more rigorously. So we started here from this integral, and we reached this point. So that integral was proved to be equal to this one. So let me write it here. Integral du nu dx nu differential of the volume equal to the integral u nu x nu over rho nu ds. And remember to evaluate this at the origin, but we will do that later. I'm not interested in that part. I'm interested here in showing how to prove this more rigorously. Actually, this is a generalization of the divergence theorem. So let's consider the divergence theorem. We have integral over a closed surface, which in this case is a sphere, but never mind, of a vector field f dot product with a unit normal to the surface ds. This is equal to the divergence of the field times the differential of the volume. Now, if we choose for the field f a scalar function that I will call, let's say, g, and then I multiply this by a constant vector field that I will call c. So remember that c is a constant, whereas g is a function, a scalar function. So if you substitute there, you will get integral c dot product with g times n. So I can rewrite it like this, and c is a constant, so I can also put it out of the integral if I want. And this is equal to integral, and then here what do I have? I have the gradient of g dot product with c dv. But what does this imply? This implies that the integral over the surface of gn ds is equal to the integral of the gradient of g dv. And this is exactly this formula up here. So let me cancel this, because the normal in this case will be only the x component of the normal. So we are interested in taking the x component of this relation. So if I take the x component, here I will have nx. On the left, I have nx, whereas here I will have the derivative with respect to x of g. And in this case, our x will be x nu. So nx is simply equal to the x component divided by the radial distance rho, x over rho, or if you want, x nu over rho nu. And this is exactly the formula that we get. So let me cancel this. I don't need all these formulas. Here, this was just for the sake of clarity. I wanted to motivate even more rigorously what we did so far, because this is more irrigorous than what we did earlier. Anyway, now let's start again from here. Then we can also put, instead of rho nu, we can put r prime, because this integral is performed on the surface of the sphere. And therefore, let me write it as a minus n integral u nu at the origin times x nu over r prime ds. And now we can also use the expression for the velocity, and in particular, we can keep only some terms for the velocity u nu. We will neglect high order terms. If you check this expression for u nu, remember it's this one with a minus sign, so we can neglect the higher order terms, this one and also this one. So we are only left with this term here. Let's go below and do our calculation. So let me rewrite u nu according to this assumption that we can neglect higher order terms. Minus 5 over 2 r cubed over, we have rho nu cubed, and we will have to replace r prime cubed here. And I also multiply by 1 over rho nu squared, because there was rho nu to the 5th power here. Then we have xi nu a xi nu squared plus b era nu squared plus c zeta nu squared, like this. And at the origin, xi nu will become minus x nu. And all these terms will also, so they will become x nu squared plus, here we will have y nu squared, and here we'll have z nu squared. So when we substitute this expression inside our integral, we have a star equal to a minus n, and then we have integral 5 over 2 r cubed over r prime cubed 1 over r prime squared times x nu, and then we have a, let me cancel this, a times x nu squared plus b times y nu squared plus c times z nu squared. We multiply by x nu over r prime ds. And now we have to integrate over the sphere with radius r prime. So it is just a bunch of calculations. There is nothing major about this. After integration, you find a star equal to a minus n 4/3 pi r cubed, like this, which is equal to a times 1 minus n phi, or if you want, a times 1 minus phi, lowercase phi, because lowercase n will be capital N over V. It is the number of spheres per volume. Analogously, one can also find b star equal to b times 1 minus phi, and C star is C times 1 minus phi, which means that we can write the expression for delta star squared will be equal to delta squared times 1 minus phi squared. But since phi is a small quantity, we can also approximate this as 1 minus 2 phi, because we can neglect the phi squared term. Now, if we go back to the calculation of the work, we know that we can calculate it like this, but by using this dilatation coefficient delta star, we can also calculate it in a different fashion. So without the presence of the sphere, W can also be calculated as twice k delta squared V, and of course phi is equal to 0 in this case, so without spheres. With the spheres, W can also be calculated in a similar fashion as twice k star delta star squared times the volume, like this, where k star represents the coefficient of viscosity of the mixture which takes into account the liquid and also the spheres. So this work will be equal to twice k star delta star squared, which we calculated to be delta squared times 1 minus phi squared times the volume, and this is approximately 1 minus 2 phi. And from here we can calculate k star. K star is equal to k times 1 plus phi over 2 divided by 1 minus 2 phi. And this is approximately equal to, if you consider the expansion of this function, so we consider phi to be small, so this is k times, if phi is equal to 0, this is 1, and then we have plus the derivative of this function evaluated at phi equal to 0. If you calculate the derivative of that function and you set phi equal to 0, you get 5 over 2, and you have to multiply by phi. So this is the result that we obtain from these considerations. And if we go below here, I have simply calculated the formula for delta squared, but we can conclude actually. So if very small rigid spheres are suspended in a liquid, the coefficient of internal friction increases by a fraction that is equal to the total volume of the spheres suspended in unit volume, provided that this total volume is very small. Now, the formulas that we have found can also be used to evaluate molecular dimensions. In particular, we have found that k star over k is approximately 1 plus 5 over 2 phi, and this is equal to 1 plus 5 over 2, and then we have n over v, capital N over v, times 4 over 3 pi r cubed, the formula. So this is the radius of the sphere, this is the number of spheres, and this is the total volume, where this was indicated as n. This was denoted as n, lowercase n. And we also know that n divided by the Avogadro's number can be written as the mass of the dissolved substance per unit volume, that we will call it rho, like a density, and then we divide by the molecular weight, m. This is the formula that Einstein uses, and then we can rewrite the formula above like this, so you can obtain Na times r cubed equal to 3 over 10 pi m over rho k star over k minus 1, like this. Let me rewrite it properly. And Na times r is also related to the diffusion coefficient. And you can see, for example, the paper on the Brownian motion. I have also made some videos on that. And it can be shown that Na times the radius of the sphere can be written as the universal constant, R0, times the temperature, divided by 6 pi times k times 1 over d, where d is the diffusion coefficient. The two equations together enable us to calculate separately the quantities capital R, which gives us the idea of how big the sphere is, or if you want, you can try to generalize this to consider a molecule, and also Na, the Avogadro number.